Today we are going to learn about quadratic functions. And a quadratic function has a standard equation in which there is a square involved instead of just a linear term. As you can see, the standard form of a quadratic function is y equals ax squared plus bx plus c. That would be considered a quadratic function in standard form. Today we're going to investigate the graphing methods of this quadratic function. There are three forms. Right now we're just going to look at a basic quadratic function. So first of all, let's just take a look at these three graphs and see if we can determine some things about a quadratic function. We're just going to look at the basic one, where all we do is examine the a in ax squared plus bx plus c. We're just looking at this part. So notice a general parent function of a quadratic equation is y equals x squared. And that's what I have on my calculator. So let's take a look at what that looks like. Let me see if it's on. There we go. And we have that basic U-shaped. And in that U-shape, we call that a parabola. So all quadratics will make the shape called a parabola, which is a U-shape. Is this parabola symmetrical? Is it the same from the left side as it is to the right side? Yes, it is. So what is that axis of symmetry? It is this axis right here, which is called the y-axis, but it is the equation x equals 0. So it will be x equals the x value of your vertex. And my vertex is right here, 0, 0 on the standard equation. Let's investigate what that a does. First, we're going to try positive 1/2 x squared. There's the parent. There's the 1/2 x squared. Notice the positive. It's still opened up, but what's the difference between a 1x squared and 1/2 x squared? This is the 1x squared. This is the 1/2 x squared. The 1/2 went wider. Now let's investigate the 2. There's y equals x squared. Y equals 2x squared. So the positive still opened up, but the 1 to the 2, 1 to 2, the 2 got narrower. So a positive a will open up. An a between 0 and 1 will be wider. That was the 1/2. This was wider. An a greater than 1 got narrower. Now let's investigate these. Again, I have the 1x squared, but this time I have a negative a in both cases. So let's try the negative 1/2 squared. So let's turn that one on. There's x squared. There's negative 1/2 x squared. The negative opened down. Did the 1/2 still get wider in here than the 1? Yes, the negative opened down. So let's see what the negative 2 does. There's 1x squared, negative 2x squared. Negative still opened down. Did the negative 2 get narrower in here than the 1? Yes, it did. So it still holds true. When a is between 0 and 1, it's wider. When it's bigger than 1, it's narrower. But when a is negative, it opens down. Now let's investigate by adding in a bx and a c term. So we're going to look at these three. So again, I have my regular parent function of x squared. And then I have x squared minus 8x plus 16. There's x squared minus 8x plus 16. Notice this x squared vertex was 0, 0. X squared minus 8x shifted it 4 to the right. So this vertex was 4, 0 when it was a minus 8x plus 16. Let's see what plus 12x plus 36 does. And I want to turn this one off. There's x squared plus 12x plus 36. Again, x squared's vertex was at 0, 0. X squared plus 12x plus 36 went 1, 2, 3, 4, 5, 6 to the left. So this one was negative 6, 0. Do you see a relationship between negative 8 and 4? Between positive 12 and negative 6. Negative 8, 4. Positive 12, negative 6. It's looking like this b term. To get the vertex, we would take half of the b term and the opposite sign. So opposite of b over 2. Half the opposite of b. Let's see if that holds true when I have a coefficient other than 1. So notice I kept my b terms both at negative 4x, and let's see if that a has a difference. So here I want 2x squared minus 4x plus 0. Just a moment. Let's clear this one out. There we go. X squared, 2x squared minus 4x. Notice my vertex is 1, negative 2. So this idea of the opposite of b over 2, let's see, I had 1, negative 2. Half, opposite of 4 is 4, halved is 2. But I still got 1. Does that 2 have a play in it? Let's see if I put the plus 1 on the back. X squared, 2x squared minus 4x plus 1. Oh, that shifted it still over 1, but down 1, negative 1 instead of negative 2. This is still 1, but now it's negative 1. So do we still have this opposite of b over 2? How about 2 times a? 2 times 1 would have given me that. The opposite of 4 would be a positive 4 over 2 times 2 Would that give me my 1? It does. Works on both of these. So what that means is that I have the opposite of b over 2a, and to get the y value, I simply stick that x value into the function. So here, when I did the opposite of b over 2a for x, I got 1. When I take that 1 and I substitute it into this function, I get y equals 2 times 1 squared minus 4 times 1. That's 2 minus 4. That's negative 2. So it did give me the vertex 1, negative 2. So in standard form, when I have all the bx plus c added into that ax squared, I will find the vertex by taking the opposite of b over 2a. And then once I have that x value, I'll stick that into the function and solve for y. So we are going to use this idea of this parent function every single time we graph. Here's that parent function graph, that y equals x squared. So let's take a look at some parent functions, since this is kind of our first time really doing that. When you have a parent function, it is the function equals x and whatever was done to the x value. There will never be an a, h, or k in the parent function. We'll just simply look at what operation mathematically was done to x. So let's take a look here. My function is 3 times the absolute value of x minus 2 plus 4. This is one we did in chapter 2. So when we look at that, we're going to take away the a, the h, and the k. So all that would be left for a parent function is f of x equals the absolute value of x. Here we have 3 times x minus 2 squared plus 4. To get the parent function, again, we're going to take away the a, h, k. And we would have y equals x squared, which is what we just got done looking at the basic graph of all the y equals x squareds. Let's look at this one. Again, take away the a, the h, and the k. And my parent function would be y equals x cubed. Now let's go back and look at the a's of all those. These a's were always 3. In every situation, I kept it the same. So let's try this parent function. Again, a is 3. If I take away the a, the h, and the k, can you tell me what the parent function would be? F of x equals x to the 1/2 power. See how we get the parent function? Take away everything else except what was done to x. So our parent function was right here. This is the one we're studying for quadratics. Y equals x squared. So when we're looking at that, we want to again examine this graph. We had a vertex of 0, 0. Then we had the point 1, 1. Symmetrically, we had negative 1, 1. We had 2, 4. Symmetrically, we would have negative 2, 4. If we wanted to keep going, we had 3, 9. Symmetrically, we'd have negative 3, 9. These came from y equals x squared. 0 squared is 0. 1 squared is 1. Negative 1 squared is 1. 2 squared is 4. A negative 2 squared is 4. 3 squared is 9. Negative 3 squared is 9. And we will always use that parent function. So let's go back and look at our a, which was a 3. I am still going to stick in the x value of 0. And then I will square it, add 4, and then multiply by 3. So this is a multiplier. So a is a multiplier. So it will end up tripling our y value. Because I still put a 0 in for x, so I still got a 0 here, but in the end, I'd have 3 times as much on my y value. So when I do that, I am going to, since a was 3, triple my y's. So I take this 0 and triple it, I get 0. 1 tripled is 3. 1 tripled is 3. 4 tripled is 12. 4 tripled is 12. So a will multiply and stretch our y values. So let's try our first graph. Y equals 1/2 x squared minus x minus 6. And we should always ask ourselves these questions. Since a is a positive 1/2, will the graph open up or down? Positive a's open up. It's in standard form. So to find the standard form, we said x has to be the opposite of b over 2a to find the vertex. So what is b here? It is negative 1. So the opposite of a negative 1 is a positive 1. Over 2 times a was 1/2. That's 1 over 1 is 1. So the x value is 1. Now I take that 1 and plug it into my function. So I have y equals 1/2 1 squared minus 1 minus 6. That's 1/2 minus 7. That's negative 6 and 1/2. So now I can plot the point 1, negative 6 and 1/2. My axis of symmetry will go right down the middle of that vertex, which is x equals 1. Your axis of symmetry will always be an equation that reads x equals the x value of my vertex. Now we're going to use our parent function. Remember, this was the graph of our parent function. Also remember, it gave us the values where y equals x squared. 0, 0, 1 squared 1, negative 1 squared 1, 2 squared 4, negative 2 squared 4. So we will always use these values. Do we have a multiplier? Yes. So now our multiplier is 1/2. So we take 1/2 times our y value. Half of 0 is 0. Half of 1 is a half. Half of 1 is a half. Half of 4 is 2. Half of 4 is 2. So from this point, I've shifted my vertex over to here. From that point, I'm going to, there'd be my 0, 0 of my new axes. Then I would plot 1, 1/2. So I go 1, 1/2. Negative 1, 1/2. Negative 1, 1/2. 2, 2. 1, 2. 1, 2. 1, 2, 1, 2. And I would have 5 points that I should be able to now draw my vertex through, or my parabola through. Let's investigate another form. It is the form that is called vertex form. The reason it's called vertex form is because it is in the form y equals a minus times x minus h squared plus k. Notice it is in the x minus h squared plus k. The vertex will always be h and k. So it's what's behind the minus sign and what's behind the square. The axis of symmetry then will be x equals h, because it has to be the x value of my vertex, which is h. So I have a couple graphs here. Remember our parent function started here at 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. There's my parent parabola. Look here. What is h and k? 2, 3. So my vertex shifted over right 2, up 3. And I have my blue vertex. Do I have a multiplier? A is 1. So no, I don't have a multiplier. So 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. So from here, I can make my new axes, and I have 1, 1, negative 1, 1, 2, 4, negative 2, 4. And I get my blue parabola. Let's look at the green graph. Here's h, here's k. So again, 2, 3. So if I take my parent function of 0, 0, shift right 2, up 3, I end up with the same vertex, 2, 3. But this time, my a is 1/2. So do I have a multiplier? Half my y's. 0, half of 1 is half, half of 1 is half, half of 4 is 2, half of 4 is 2. So 0, 0. Got that plotted green. 1, 1/2. 1, 1/2. Negative 1, 1/2. 2, 2. 2, 2. Negative 2, 2. And I have my green parabola. So we can use the vertex form to shift my vertex right from the equation. So let's try one. We're going to graph y equals 2 times the quantity x minus 1 squared plus 3. Again, will this parabola open up or down? It will open up because a is a positive 2. What is the vertex? In this form, what is h and k? H is 1 and k is 3. So plot the vertex 1, 3. Right 1, up 3 would be my transformation. Then draw your new axes in there. My parent function is y equals x squared. So when I make my xy table, 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. Do I have a multiplier? Yes. So it should double my y's. 2 times 0 is 0. 2 times 1 is 2. 2 times 1 is 2. 4 times 2 is 8. 4 times 2 is 8. 0, 0. Already have that plotted. on my new axes. 1, 2. 1, 2. Symmetrically, negative 1, 2. 2, 8. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Symmetrically, negative 2, 8. And I should be able to graph my parabola. So what was our axis of symmetry? Our axis of symmetry was right here through x equals 1, which matches my vertex, x. Now let's try one last form, and that is called, here's standard form, one for us to try. So, in standard form, will this open up, or, the same graph. Let's try our intercept form, the last form. Here we go. In this form, y equals ax minus p and x minus q. Where the x-intercepts, that's where it crosses the x-axis, are p and q. X-intercepts, p0, q0. That's how you know where it crosses the x-axis, because it is those points. So we must list the intercepts as points. Then, the axis of symmetry would be halfway between. So I would have p plus q over 2, x equals. That will be my axis of symmetry. So let's take a look at the blue one. I have x minus 3 and x minus 5. If I have x minus 3 and I want to find the 0, where y is 0, I would add 3, so I would get x equals 3. So this is the point when x was 3, the y was 0. Let's see if I can get that in there. So this one, x minus 5 equals 0. Add 5, x equals 5. So when x is 5, the y was 0. So I have 3, 0 as a point, and I have 5, 0 as a point. So halfway between there, I'm going to take 3 plus 5 and divide it by 2. 8 divided by 2 would be 4. So the x value is 4. To find the y value, I must plug in. So my vertex will be p plus q, my two intercepts, divided by 2, and then f of that, which means you plug the x value into the function. So y equals 4 minus 3 times 4 minus 5. 4 minus 3 is 1, times 4 minus 5 is negative 1. 1 times negative 1 is negative 1. 4, negative 1 is my vertex. And does that follow? Do I have a multiplier? No, it is 1. So from here, over 1, up 1, over 2, up 4, and symmetrically. Does it all still follow? Now let's try the red one. Again, my intercepts are from x minus 3 and x minus 5. So will I have these very same intercepts? Yes, 3, 0, 5, 0. But now, when I plug that into my equation, I get y equals 2 times 4 minus 3 times 4 minus 5. That's 2 times 1 times negative 1. That's negative 2. So my vertex on the red one is 4, negative 2. 4, negative 2. Do I have a multiplier on this one? Yes, I do. So my parent function of 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4, my multiplier would be 2y. 0, 2, 8, 2, 8. So 0, 0, 1, 2, 2, 8. 5, 6, 7, 8. And symmetrically. Did I get those same points? Yes, I did. So let's try a graph in intercept form. How do I know this is intercept form? Because I have all of these factored. My A is a positive 2. So my graph should open up. My vertex has to be halfway between my intercepts. So let's find one of my intercepts. X minus 3 equals 0. Add 3, x equals 3. 3, 0. One of my intercepts. My other intercept will come from x plus 1. And that equals 0. Subtract 1, x equals negative 1. Negative 1, 0. So to find my vertex, I have to go halfway between these. So x will equal 3 plus a negative 1 divided by 2. 2 divided by 2 is 1. Halfway between, the x value would be 1. So y, I'll have to find by putting in a 1. So I would have 2 times 1 minus 3 is negative 2, times 1 plus 1 is positive 2. 2 times a negative 2 is negative 4, times 2 is negative 8. 1, negative 8. 1, negative 8. So again, I would create my axes here. And I use my parent function. Do I have my multiplier? Yes, of 2. So this becomes 2y. 0 doubled, 1 doubled, 1 doubled, 4 doubled, 4 doubled. So I have my 0, 0 plotted. 1, 2. 1, 2. And symmetrically, negative 1, 2. 2, 8. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 8, symmetrically. Graph your parabola. So my axis of symmetry happened right here, which is x equals 1. So now you should be able to graph in standard form, vertex form, and intercept form. Again, let's just review those quickly. Standard form, f of x equals ax squared plus bx plus c. To find the vertex, you take x will be the opposite of b over 2a, and the y value of the vertex will be to plug that x value into the given function. In vertex form, f of x equals a times the quantity x minus h squared plus k. And the vertex is hk. And in intercept form, f of x equals a times x minus p times x minus q. where P0 and Q0 are the x-intercepts. Your vertex is found by taking P plus Q divided by 2 for your x value, and your y value will be taking that x value and putting it in my function. And no matter what, when I graph, I use the parent function y equals x squared. So it's 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. And from there, I check out my a, and I multiply it by my y's to continue with my points to plot.